Welcome to this video tutorial. Today we will learn about three topics: pulse amplitude modulation, time division multiplexing, and quantization. Let's start from pulse amplitude modulation. This is a hierarchical chart of types of modulation. As you can see, first division is based on the type of carrier, that is, whether it is a continuous wave carrier or pulse carrier. Then pulse modulation is divided into two parts: analog modulation and digital modulation. And pulse amplitude modulation comes under analog modulation category. In pulse amplitude modulation, amplitude of the pulse carrier varies proportional to the instantaneous amplitude of message signal. As you can see, this is a message signal and a carrier pulse train, and ST is a Pam signal. It is clearly visible that amplitude of carrier varies according to the message signal in ST. So this is pulse amplitude modulated signal. So our aim is to generate Pam signal and recover the message signal from it. We will perform each operation in the order shown in the block diagram. First of all, we will take a message signal MT and we will perform flat top sampling on it. Then we will finally recover the message signal. In flat top sampling, the top of the samples remain constant and is equal to the instantaneous value of the message signal xt at the start of the sampling process. This is an example of flat top sampling. Generation of Pam signal involves two steps. In the first step, we will do instantaneous sampling of the message signal every ts seconds. Here, sampling rate is chosen in accordance with the sampling theorem. This is an impulse train. We will use it for ideal sampling. Ideal sampling of this message signal with the previous impulse train will give us this m delta t signal. The instantaneously sampled version of mt is given by m delta t. Here, delta t minus nts is a time-shifted delta function. Now comes the second step, that is, lengthening the duration of each sample to some constant value t. Initially, we had an impulse dt. Now we want to stretch it to some constant value t. Suppose we pass it into this function to meet a requirement. Now the output is a rectangular pulse of width t from minus t by 2 to t by 2. Its frequency response can be given by this function. So the transfer function hf can be written as this. Now we had m delta t, and to stretch it, we will pass it into this transfer function. So our flat top signal will be represented by this function in frequency domain. Mathematics behind the previous operations in time domain. After the instantaneous sampling of our message signal MT, we got m delta t. Now for stretching the samples, we will convolute it with HT shown in the previous slide, and the resultant will be our Pam signal ST. Substituting the value of m delta t, we will get this equation. Here we are using the property of delta function. Finally, we got ST, which is our pulse amplitude modulated signal. This is our generated Pam signal in time domain. Two steps involved in the generation of Pam signal, which were the instantaneous sampling and the lengthening of samples, are collectively known as sample and hold. Since we have generated the Pam signal, now our next aim is to recover the message signal MT. For that, let's do some analysis in frequency domain. Suppose our message signal MT is band limited to a frequency of FM. Then its Fourier transform will be this MF. Instantaneous sampling with ideal pulses will result into m delta t, and its Fourier representation will be m delta f. Now, from the equation we know that our Pam signal in frequency domain will be multiplication of this sinc function and m delta f. This is the sinc function and this is m delta f. So our SF will be this. Now passing this through a low pass filter, we will get a recovered message signal MRF. This is our recovered message signal MRF. We can therefore see that using flat top samples to generate Pam signal, we have introduced amplitude distortion. This was because the Fourier transform of rectangular pulse was a sinc function. So it is not flat here. We can reduce this distortion if this tau is very less. This distortion is known as aperture effect. This can be corrected by using equalizer. The equalizer has the effect of decreasing the in-band loss of the reconstruction filter as the frequency increases in such a manner as to compensate the aperture effect. We have completed pulse amplitude modulation. Now let's start time division multiplexing. Multiplexing is a method by which multiple analog or digital signals are combined into one signal over a shared medium. This diagram shows multiplexing. And in time division multiplexing, the basic parameter over which we do multiplexing is based on time. Now we can see that the sampled Pam waveform is off for most of the time. During the off period, the channel can be used to transmit samples of other waveforms. The concept of merging samples from several signals into a single waveform is called time division multiplexing. Here we can see that we have merged samples of two different signals into a single waveforms. This white colored sample is from signal 1 and the blue colored samples are from signal 2. So this is an example of time division multiplexing using pulse amplitude modulation. Now let's understand this by block diagram. Here we have multiple signals and then we will pass them through low pass filters. These low pass filters will act as anti-aliasing filter so that the bandwidth of signal do not merge with respect to consecutive signals. Thereafter we have switches. The switch at transmitter is known as commutator and the switch at receiver is known as decommutator. Here this commutator will first connect to signal 1 to send sample of signal 1, then this commutator switch will rotate and next time it will be sending sample of signal 2 and so on. And that is what we give to pulse modulator. This is transmitter block diagram. Now let's see the complete process. The first sample of signal 1 will come here and if the commutator is connected to the signal 1 then this sample will go over there. Now the commutator will rotate and sample of second signal will come and if it is connected then this sample will go over the pulse modulator and so on. Now these samples will pass through communication channel and then they will go to the pulse demodulator. When the samples comes to demodulator, we will have same sequence of samples over here. The decommutator is synchronized with the commutator. So both have the idea about which sample is coming from which signal. The switch will rotate and this will send the first sample over here, the second sample over here and so on. Now since the cycle repeat, we will get our signals here. Multiple samples of each signal will come and we will process them through low pass filter and then we can extract our signals. So this is how multiple signals share the same medium for communication. We have completed time division multiplexing. Now let's start quantization. Quantization is the process of mapping input values from a large set to output values in a smaller set, often with a finite number of elements. Now we will see why do we need quantization. So, Even if we have digital signal, we are still in a domain where there are a lot of amplitude values that the receiver has to detect. So, since there is no limitation on the number of levels, it becomes very complex on the receiver side. Plus, if if there is noise involved in the signal, then having multiple values of amplitude creates trouble, as we don't know what value we should take. For example, here we have noise here, so we don't know what value we should take in this range, whether we should take 2.2, 2 or 1.8. So we do quantization. So quantization limits the work that the receiver has to do and it decreases the noise. Now let's do the quantization. First of all, we will take the analog signal GT. Now, before we proceed with quantizing the amplitude of this given signal, we would first sample the time axis uniformly with a sampling interval of Ts so as to avoid any irregularities on the time axis while quantizing. We start by comparing the lowest level's value and GT's value on the first sample time value. If the function's value is greater than the current step size value, we jump one step above, given the current one is not the highest level. If so, we remain on the same step. Whereas, if the function's value at the current time value is lesser, we jump one step down, given the current one is not the lowest level. If so, we remain on the same step. As we can see, GT's value at first sample time was greater than the first level, so we jumped one step size above and maintaining the same level's value, we horizontally move towards the next sample value of time and do the same. Now, GT's value is less than the current level at the current time value, so we jump down and hold the new value to the next time sample. Performing the same steps for all the samples of the original analog signal will generate quantized signal. Since the quantized version of any function gt, that is gqt, doesn't include every detail of the original function, thus giving rise to an error function which at any instant of time is defined as gt minus gqt. The maximum error at any level can be equal to half of the step size. In order to reduce the error between actual and quantized signal, the step size used while quantization should be as small as possible. As we reduce the step size, there arises a condition when the noise of the level might become greater than half of the step size, and in that case, we may map that sample to any other level, hence creating unnecessary noise. Hence, selecting optimal step size is always a trade-off, as lower step sizes might create interference of noise with levels and higher step sizes lead to more error in the actual and quantized signal. We have now completed all the three topics that we wanted to cover in this tutorial. Thank you.